Hello, nice to meet you guys. I'm Danny. Today I want to talk to you guys a little bit about root finding in Rust. So what is root finding? And another question we had was how does it compare to optimization? So root finding is where we try to find the inputs where a function's output is zero, or where f of x is equal to zero. And problems solved through root finding need to be formulated such that the point of interest crosses through the x-axis. As for optimization, we're interested in finding maximums and minimums of certain conditions. For example, a function like where x is the derivative of f is equal to zero. Problems solved through optimization need to be formulated such that our point of interest needs to be at the minimum or the maximum of that function we're trying to solve. Okay. So what we want to try to apply root finding and optimization to was this problem of cohesive zone models. And our objective was to identify the stable equilibrium within the cohesive zone model. And we have two methods that we went about doing this through the traditional Newton's root finding method and the minimization optimization method. In the next slide, we'll see a little bit of a visualization of how that root finding method can be illustrated with a red dot representing Newton's and the green dot representing minimization. And the reason why this problem is so interesting is because it is able to be formulated in both a root finding and an optimization problem. So for those who are unfamiliar with cohesive zones depict an object formulating a crack as you begin to tear it apart. Sort of imagine like having like your material stuck to a wall and it's stretching it out slowly and slowly before it breaks. So in this cohesive zone model, in this GIF, you can see the dots slowly climbing up to the point right at the top there before they jump down. And that would sort of represent that breakage that happens where if you're like pulling on an elastic material, it suddenly snaps and comes off the wall. And we can see the red and green dots slowly rising up to this point before they jump over there. We're not interested in these roots necessarily because those aren't the stable equilibriums. And after we cross this point here, we're interested in the answer being found over on this side at that jump. Over on the left side, there's a function that depicts the integral that needs to be minimized as we begin to solve for that optimization problem. So two libraries we were exploring to solve this problem were Argmin and PETSc. So Argmin is a pure Rust, aside from ND array linalg, which is based on Blaze, loss, and laypack, and it has a trait-based interface, which is traits for gradients, Hessians, etc. And it calls code by specifying solution algorithms within the code, and was started in 2017 with over 625,000 downloads. PETSc-rs is Rust bindings for the PETSc library, which is written in C, and the PETSc library has been around since 1994, while PETSc-rs is more recent. So a little bit about why we're interested in PETSc. It has some mature support for linear algebra through the PETSc library, which has been around for quite a long time. And we can define systems and closures through our PETSc bindings, and then the solution algorithms can recursively be composed at runtime. And we can also set observers at runtimes with distributed memory parallelism and GPU support. This image on the right here showcases how a user might define some user-defined options for, say, if they want to have a verbose flag or if they want to define constants within their code. And one nice thing about PETSc is that on top of defining your own user-based options, you also get a set of options that come with PETSc itself. Like, for example, if you wanted to adjust like mentioned before, if you wanted to like add more observers to log the norm or the residuals that come with your root finding or optimization. I'll let my co-presenter Owen White present now.
Awesome. Thanks, Danny. And for Argmin, a lot of the advantages we found is it leverages Rust's pretty strict type system and with the traits that it allows you to create for cost function, gradient, and Hessian, so that at compile time, you know that I have the required data for my solver to be able to converge accurately. And also these traits help to implement new solvers within Argmin. As you can say, I need the gradient and the Hessian for my solver to work. And so you tell basically the Rust compiler that the user must have these two traits implemented to be able to use my solver. And observers are specified at compile time. And this is pretty beneficial just because it lowers like overhead at runtime for like determining how you're going to observe the solver. And that also kind of goes for all options being determined at compile time. And another big part of Argmin is that it is feasible, relatively feasible, to adapt to no standard. So which allows you to use GPUs, which is very important for high performance scientific computing. Currently, we have been working on getting faer, which is a dense linear algebra API designed sort of to be akin to BLAS LatePack and the back end, so that we can take Argmin away from that ND-array linalg dependency and bring it into the pure Rust space. And it is shown through benchmarking that some of these newer routines can outperform for higher dimensional matrices. And I have some kind of rudimentary benchmarks there at the bottom that shows in 1,000-dimensional Rosenbrock and a 3,000-dimensional Rosenbrock, where there's fairly significant performance increases just at the those dimensional levels. And another big part that faer does that ND-array linalg kind of struggles with, I guess for our specific problems, was that faer can perform these inverse matrix operations in place, which removes an allocation in the Newton steps, which is pretty big for performance. And that is reasonably why we expect the performance gain that we achieved. And looking towards the future, in these Newton steps, we would prefer to not compute the inverse of the matrix. We'd rather just back solve on an LU decomposed matrix. And I've got a couple flame graphs I'll show you here that sort of depict why maybe we don't want to do that. This is the one you're seeing right now, the flame graph, which is just an output of kind of what the CPU is doing, and the width is proportional to how long it was running. But this is for an 100-dimensional one, and it's spending most of its time computing the LU inverse and not that much time inverting matrix, which makes sense because it's not that difficult to invert such a small matrix. However, when you switch to a larger matrix, I think this was the 1,000 or 3,000-dimensional flame graph output, you can see that it spends much more of its time trying to compute that inverse than it does computing the LU decomposition. And so if we can sort of optimize that inversion, that matrix inversion out, we can free up a lot of the performance and make it, I guess, yeah, more performant. And another big area we were tackling, especially with this cohesive zone problem, is interoperability between Argmin and PETSc, and sort of being able to say, if I have my model built in Argmin, can I also use PETSc solvers to solve that model? Or if I have my model built in PETSc, can I also use Argmin solvers for that model? And so this came down to a lot of sort of enforcing things on a PETSc model versus sort of trying to gain information from an Argmin model. Because from Argmin to PETSc, it was a lot of just, it was not as difficult because we had to, we already had all the information there, I suppose, and we just had to make sure that it was getting into PETSc correctly through setting the DM and setting all of the optimization, or not the optimization, all of the boundary conditions correctly. And then from PETSc to Argmin, it was a little more challenging, and I think we're still working on that. But because Argmin requires a lot of that stuff at compile time, and PETSc allows you to set a lot of the information at runtime, and so being able to accurately say to the Argmin solvers that we have this information is a little bit more difficult. And I think that, yeah, that concludes our presentation. So yeah, we just like to say thank you for having us and allowing us to present here.
Thank you very much, guys.
Thank you, Daniel and Owen. Are there any questions for either of them? I've got some coming in on the Q&A, if you guys can see that.
Sure, using an algebra with Argmin. Argmin actually comes bundled with an algebra, and a lot of that, and that's sort of baked in, and that's why it's maybe not it's not no standard quite yet. So it already actually has that baked in. We weren't switching the matricy types or anything to faer. We were just trying to change the way it computes the inverse.